type a simple query into the world's most advanced artificial intelligence. How many times does the letter R appear in the word strawberry? The engine, capable of passing the bar exam and writing complex code, will confidently answer 2. This is not a temporary glitch. It is a symptom of a fundamental structural blind spot. We assume these systems build a continuous, human-like understanding of our language. But at the very entry point of their minds, there is an invisible filter, an abstraction layer that alters everything they perceive. The machine did not miscalculate. The machine literally cannot see the letters. We assume that when we type text into a neural network, it reads the words just like we do. But the machine is functionally blind to our alphabet. Before a single artificial neuron can fire, human language must be fed through a digital preprocessor called a tokenizer. The tokenizer is a translation layer. Its sole job is to take our rich, messy human language, slice it into arbitrary mathematical fragments, and map those fragments to a sequence of numbers. When you type strawberry, the model never receives the letters. It receives a list of numerical IDs representing pre-cut subword chunks. Because the system is blind to the characters inside those chunks, it has no native way to count them. It is forced to guess based on statistical associations, predicting the spelling of a word it has never actually seen. To understand how this happens, imagine a printing press that has run out of individual metal letters. Instead of having single stamps for individual characters, the printer only has pre-carved blocks containing common combinations of letters seen in previous texts. This is byte-pair encoding, the algorithm behind almost every major language model today. The tokenizer starts with basic characters, then scans billions of pages of text, merging frequently adjacent characters into permanent, single blocks. Over time, it builds a massive static library of these pre-carved fragments, usually containing between 30,000 and 100,000 tokens. When a new sentence arrives, the tokenizer slices the text using the largest blocks available. For the word strawberry, it might only need 2 blocks, straw and berry. To the neural network, strawberry is not a 10-letter word. It is simply token 4,930 followed by token 8,291. The individual letters are sealed inside those blocks, entirely hidden from the machine's active reasoning. Because these digital block libraries are built by analyzing datasets heavily dominated by Western web traffic, they are fundamentally optimized for English. In English, the tokenizer has learned highly efficient, whole-word blocks. One word almost always equals a single token. But if you write the exact same sentence in Hindi, Japanese, or Amharic, the tokenizer struggles. Lacking pre-carved blocks for these character sets, it is forced to shatter non-Western words into tiny, fragmented subtokens or raw bytes. A simple phrase that costs 3 tokens in English can easily cost 15 or 20 tokens in Tamil. This is a structural bias built into the very bedrock of modern artificial intelligence. The machine is mathematically faster, more coherent, and more expressive in English because its raw perception of other languages is fractured. This bottleneck translates directly into a global economic disparity known to developers as the token tax. Because major AI providers charge API customers based on the volume of tokens processed, running an application in a non-English language is drastically more expensive. A developer in Nairobi building a Swahili medical tool, or a startup in Tokyo deploying a Japanese assistant, pays up to 10 times more than an English equivalent for the exact same computational output. They are paying a premium for the inefficiencies of a translation layer they did not design. This token tax quietly penalizes global innovation, forcing non-Western developers to operate with shorter context windows, higher latencies, and vastly inflated operational costs. In 2022, Google researchers published a paper detailing PaLM, a monumental language model boasting 540 billion parameters, trained across more than 6,000 state-of-the-art TPU chips using their Pathways system. It was the absolute peak of the brute force scale era, proving that massive computing budgets could yield incredible cognitive emergent abilities. Yet, despite this staggering concentration of raw power, PaLM was still fundamentally constrained by the exact same bottleneck. Before its parameters could process a single word, human language had to be sliced up by a sentence-piece tokenizer. This reveals a critical truth. Scaling the size of a digital brain cannot fix a compromised sensory organ. You can build a supercomputer that consumes megawatts of power, but if its input mechanism feeds it a fragmented, distorted view of language, it will still stumble on basic spelling, string manipulation, and multilingual reasoning. Because this mathematical translation layer is frozen during training, it creates structural blind spots that can act as cognitive landmines. During the creation of early GPT vocabularies, the tokenizer analyzed massive internet datasets and identified a bizarre, repeating sequence of characters from an online forum. It designated this sequence as a single, dedicated token, solid gold Magikarp, the username of a Reddit user. But because the neural network itself was almost never exposed to this word in its actual training dataset, the model had no mathematical context for it. When users typed solid gold Magikarp, the model would suffer immediate failures, outputting nonsensical code, bizarre insults, or entering endless loops. It is the danger of an artificial vocabulary. The tokenizer creates entry points that the brain cannot comprehend, leaving silent vulnerabilities waiting to be triggered. For nearly a decade, tokenization has been accepted as a necessary compression hack to keep transformer models computationally viable. But as we move toward advanced, autonomous agents that must write flawless code and process global data, this structural bottleneck is becoming unacceptable. The cutting edge of machine learning is actively researching token-free, byte-level architectures. Systems like Meta's Megabyte and emerging state space models aim to bypass the tokenizer completely, reading raw bytes of text, audio, and pixels directly. When an artificial intelligence can perceive human language natively, without a crude middleman slicing up its reality, the strawberry paradox disappears. It will see every letter, understand every language with equal fidelity, and process information without distortion. Only when we dismantle this invisible filter will we build machines that truly read our world, rather than merely calculating our patterns.